Today we're going to implement a very interesting machine learning project. We're going to use EEG data, so time series data representing brain activity, to predict whether a person is sleeping or not. And if they are sleeping, we're also going to predict the actual sleep stage. We're going to use PyTorch for this, and we'll train a deep convolutional neural network, so you can learn a lot by implementing this project. Now, if you like this video, make sure to hit the like button and subscribe, but now let us get right into it. Alright, so we're going to work with medical data in this video today. To be precise, we're going to do sleep stage classification using the Sleep EDF database. You will find a link to this page in the description down below. This dataset contains information or data on multiple subjects, and for each subject, we have two types of files. One is the PSG files and the other one is the hypnogram files. The PSG files contain 7 channels of time series data, 2 of which are EEG channels. This is what we're going to focus on. There's also other data like body temperature, for example, which we will ignore. And then we also have the hypnogram files. These contain the ground truth, so the actual sleep stage during specific time spans in the data. Now, to get this data, what you want to do is you want to scroll down here. You can either download the zip file. In my case, the download was quite slow. Or you can use wget or the AWS CLI, which is what I used. So you have to install the CLI. I'm not going to cover this in the video today, but then you can basically just pull the data from the S3 bucket with a pretty decent speed. So once you have the data on your system, you want to put it into your working directory. In my case here, I have a data directory, and in this data directory, we have all the files. The important directory in here is the sleep cassette. This is the directory that contains all the files. We can go in it and see what it looks like. We have all these EDF files. We can see some identifier, then PSG and hypnogram. So these two, for example, belong together. Now, to set up the project, you can use whatever tool or virtual environment you want. You can use the default VN from Python. You can just use your system Python installation. In my case, I'm going to use UV, the Rust-based Python package manager. I'm going to say UV init, and then I'm going to say UV add. If you're not using UV, you want to say pip or pip3 install. But we're going to need some packages here, so I'm going to say UV add, and we're going to install NumPy for working with arrays efficiently. We're going to install matplotlib for visualizations. We're going to use scikit-learn for preprocessing or train test splitting and evaluation. We're going to, of course, install Torch, so PyTorch for the deep learning, and a package that maybe you are not familiar with, MNE. Now, MNE is an open source Python package for working with EEG data, and we're mainly going to use it to load the EDF files. So to load the annotations from the hypnograms and to load the time series data from the PSG files. Finally, since I'm going to work in JupyterLab, I also want to install JupyterLab here. You can use the ordinary Jupyter notebooks or VS Code, whatever you want, but I would recommend an interactive Python notebook environment. So once we have all of this, I'm going to say UV run JupyterLab, and this is going to open it up in my browser. So as you can see, I have here my data directory, and now I'm going to create a new Python notebook, which I'm going to call main. So let us get started with the imports now. We're going to need 2 core Python imports for finding the files by specifying the pattern. So I'm going to say import OS, so import operating system, and from glob import glob. This is for pattern matching of file names. Then we're also going to import numpy as np for working with arrays, and of course import matplotlib.pyplot as plt for the visualizations. Then of course also torch and torch.nn, so import torch.nn as an n. This is for the deep learning part. And then for train test splitting and evaluation, from sklearn.model selection import train test split, and from sklearn.metrics import accuracy score and classification report. Finally, the EEG package import MNE. So let us now get started by finding the files that we're interested in. For this, I'm going to define the data directory to be equal to data/sleep-cassette, so I don't have to always type this. And then we're going to say PSG underscore files is equal to sorted glob os path join data directory, and then every file that ends with psg.edf. Then we can copy this, and we can do the same thing for the hypnogram files, just with a difference that we're going to say not PSG, but hypnogram. So now we can take a look at that. PSG files show me the first 3 entries. There you go. We have the proper paths. And if I copy that, paste it down here, and replace this by hypnogram files, we're going to see that we have the corresponding hypnogram files. Nice. So now let us get to the first interesting portion, which is the data exploration. I'm going to add some markdown here so we know that now the data exploration starts. So what we're going to do now is we're going to load the time series data, the PSG data, and we're going to look at it. So I'm going to say here raw EDF is equal to mne.io, so input output read, and then we can read raw, and we have multiple file formats here. We're going to read the raw EDF, and we're going to do that for the first PSG file. Preload is equal to true and verbose is equal to false. So now we have the data loaded. If I take a look at raw EDF, it's not going to show me any time series data. It basically shows me some meta information. We can see the file name, we can see the measurement date, and we can see here the channels. Now it tells me here that I have 7 EEG channels. This is not correct. If I click on this, I'm going to get a pop-up here which tells me that basically I only have 2 EEG channels, the FPZ-CZ and the PZ-OZ. I'm going to explain what this means in a second here. And then we have some other stuff that is not EEG data. Also, we can see that we have a sampling frequency of 100 Hertz. This basically means that we have 100 measurements per second. Now, how can we get actual data from this EDF file? We can say EEG data is equal to raw EDF.get data. Now, to be precise, this is not only the EEG data, this contains now all the 7 channels of time series data. As you can see, 7 times almost 8 million samples, basically meaning divided by 100, that would be the amount of seconds. So in this case, we have almost 80,000 seconds of data. But if I now wanted to only get the EEG data of the first channel, what I could do is I could say EEG channel 1 is equal to EEG data and then just index 0. And then to take a look at it, I can say plt.plot EEG channel 1. Now you're going to see that this is quite a lot of data, so it's not very nice to visualize it in this way. So to make it easier, we can just say, give me the first 20 seconds, which would be 2000. Remember, we have a sampling rate of 100 Hertz, which means we have to divide by 100 to get the number of seconds or the amount of seconds. So 2000 data points is 20 seconds of data. And this is what it looks like. Now, I'm not going to get too deep into the theory behind EEGs, but what we have on the y-axis is microvoltages. So it's the difference between the different electrodes. The electrodes that we use are specified by the name here. So FPZ-CZ and PZ-OZ. These are bipolar montages, which means we have 2 electrodes on the head of a person, of a patient, and we measure the differences in voltage. So when we take a look at this, this is the 1020 system. I hope it's called that. 10-20 system is what it's written like. And basically, these are just positions, standardized positions for electrodes. Now, what you notice is that our position is not shown here. So we have, remember, FPZ and we have OZ. What we basically have is we have something in the front of the head on the forehead, which would be in the center of FP1, FP2. It would be somewhere here, FPZ, connected to CZ, and then we have PZ connected to OZ, which is at the back. So these are the 2 measurements that we take a look at. We compare CZ to FPZ, which is not shown here, and PZ to OZ, which is also not shown here. We're measuring the differences in terms of voltage, and the voltage here is microvoltage actually. But for all intents and purposes of this video today, you don't need to understand what's actually happening. You have some time series data and you want to make predictions based on it. So let us actually plot all of the data so we can take a look at the different channels we have, even though we're not going to use all of them. We're going to say here now figure and axes is equal to plt.subplots, and rows is 7 for 7 channels, and columns is equal to 1, and the figure size is equal to 12, 8. Now we're going to iterate and enumerate. So we're going to say for I axis in enumerate axes. And we're going to say here ax.plot EEG data. So that is, again, all 7 channels. And we're interested in the ith channel, so depending on the iteration. And we're going to take a look at the first 20 seconds again, and then plt tight layout. So this is going to show us all the channels. Maybe let's only look at the first 10 seconds to see this in a better way. Actually, I'm using 10,000, so it's 1,000 for the first 10 seconds. There you go. So here you can see clearly EEG data, EEG data. Now, this is also some sort of measurement. I don't exactly know what it is. If you click on it, you can see that this is actually EOG. I'm not sure what this means. I'm not a medical expert. By the way, none of this is medical advice. This is purely a programming tutorial. Don't use this to diagnose anything or something like that. But basically, you can see that we have pretty smooth signals down here. So I think this one is the temperature of the body. So we have in Celsius here, 37.2 up until 37.25. So clearly these are not EEG signals, and we're also not going to use them. We're only going to use these two channels here. So let us now actually create proper visualizations with proper labeling for these two channels. We're going to say here EEG channels is equal to, and now we need to use the exact names of the features of the channels. So EEG FPZ-CZ and EEG PZ-OZ. Then we're going to say again EEG data, so we're overriding this variable is going to be equal to raw EDF.getData, and now pix is equal to EEG channels. So this is going to only pick these two channels. Then we're going to do again figure axes is equal to PLT subplots, n rows is equal to 2, n columns is equal to 1, figure size is equal to 14. We want to have it pretty wide. 14.6. Now, since I want to have proper labeling now in seconds on the x-axis, we need to divide by the sampling rate. So I'm going to specify here fs for the sampling frequency is 100. We need to divide by 100 to get to seconds. And then I'm also going to specify capital N, which is going to be the limit. Let's say 3000 here for 30 seconds of data. And then again for I-axis in enumerate axes. Now the x data, we're going to construct it by saying NPA range. So give me the values from 0 up until n, so up until 3000, but divide this by the sampling frequency. So now every single data point is 0.01 seconds, which it was before as well, but now we actually see it in the unit of seconds. So then let's say axis plot, x for the x data, and then EEG data, I for the respective channel, and then up until n. The title is going to be set title, whatever channel we're looking at. So EEG channels, which are strings, remember, ith position. Axis.set x label is going to be time in seconds. And then the y label is going to be voltage in microvolts. So if you have the proper keyboard layout, you can say Alt and M for micro, otherwise just use a U. It's also fine for the voltage here. And then finally, again, plt.tight layout. And there you go. You can see the seconds here on the x-axis. You can see the voltage on the y-axis, and we can see the bipolar montages specified as the title. So that is going to be our input data. Let us now take a look at the ground truth, at the thing that we want to predict, at the label, so to say. For this, we're going to say annotations is equal to mne.read annotations, and we're going to provide here the hypnogram file. So hypnogram files 0. Now, what does this data look like? If I say annotations, we're not going to see much here. There's 3 values here that are actually important. One is the onset, which is the starting point of a certain sleep stage. So of course we start with the first second, with the 0th second, which starts the first sleep stage, probably waking state. And then we can see the next one starts after 306 seconds. And then 307th second is something else. So this is not the distance between the individual points. This is the timestamp where this new segment, this new sleep stage starts. If we want to see the duration of an individual stage, we can just say annotations.duration. This is going to show how long a certain stage lasts. So obviously when we start at the first second and we go up until second 306, the duration of the first phase is going to be 306 seconds. And then the most important part here is annotations.description. This is the label. So we have here sleep stage W for waking state, sleep stage 1, 2, 3, 4, and then we also have REM, which is rapid eye movement, and occasionally we also have a question mark, which is unknown or unspecified. We're just going to ignore these values. So to visualize all of this together, I'm not going to write the code here from scratch again to not waste your time. You're going to find all of the code on my GitHub. You will find the link to this in the description down below. But basically here we have the same plots as before. We have the seconds and the voltage, and then we also have the hypnogram below it. So now if we plot all of this together, you can see the entire time series, both channels, and down here you can see the sleep stages. So waking state, waking state, waking state, at some point then sleep stage 1, 2, 3, and then we have some fluctuation, but basically the person slept during this time for the most part, and then they were awake again. So I think we explored enough of the data. Let us get into preparation. So I'm going to add here a markdown heading data preparation. Now I'm going to do two things here. One is going to be training the model on a single channel. For example, we're just going to use the FPZ-CZ channel to predict the sleep stage. And then we're going to use both channels to see if we get better results using both channels as compared to just a single channel. So I'm going to say here now single channel, because it makes a difference in terms of how we prepare the data. So first of all, if I take a look at the length of the file, so how many files do we have? How many subjects do we have? We have 153 subjects. This would actually blow up my RAM, so we're not going to use all of them. If you have better hardware than me, you can try to train on the entire set, or you can use some techniques to split the load if you want to. But I'm just going to use the first 20 or 30 subjects. So we're going to define a list called X data. We're going to define an empty list called Y data. And then we're also going to define a window length. So how many seconds do I want to take a look at the data to determine whether the person is sleeping or not? In my case here, I'm going to say window length is equal to 3000, which means we take a look at 30 seconds of data to determine whether a person is sleeping or not and what sleep stage they're in if they're sleeping. Okay, and now we can iterate over the subjects that we want to use. So I can say here for PSG file, hypnogram file, in zip, we zip them together, PSG files. Now I'm going to use the first 25, let's say. So also hypnogram files 25. And for each of these subjects, we're going to load the data. So I'm going to say raw EDF is equal to mne.io.read raw EDF, PSG file, preload equals true, verbose equals false. And then we're going to say EEG channel 1 is equal to raw EDF.get underscore data, pix is equal to, and now we're just going to say EEG FPZ CZ. As I said, we're going to use a single channel first. Later on, we're going to use both channels, but for now, we're going to go directly to the annotations, which are, of course, MNE read annotations based on the hypnogram file. So we pass here the hypnogram file. And now we need a dictionary to map the actual description values. So we saw we have sleep stage 1, sleep stage 3, and so on. We need to map these to numbers. So what we're going to do, I actually did it up here already. We're going to do it down here again. Now I'm going to also explain it. Sleep map, or actually let's call this stage map, is going to be equal to a dictionary mapping the individual strings. So I type this out now. Sleep stage W is 0. So this is the waking state. Then sleep stage 1 is 1, 2 is 2, 3 is 3, 4 is 4. And then R, which is REM, is going to be 5. And actually I need to unindent this. But now we get to the interesting part. Now we construct the actual data segments. So we're going to say here for I, and now we're going to do something fancy. We're going to enumerate and we're going to zip. So I'm going to have here onset, duration, and description. And this is going to be in enumerate, zip, and then annotations dot onset dot duration dot description. So let me zoom out so you can see what I'm typing here. We basically have for I, onset, duration, description, enumerate. This is where the I comes from. And then zip, we're zipping all of these together. I need one more closing bracket here, but basically we're zipping them together and we're getting them here as onset, duration, and description. Now, if the description is not part of our map, we're going to just continue. We're going to just ignore it. For example, if it's a question mark, we're going to say here, if description not in stage map, which means not in the keys of stage map, then we're going to just say continue. And now we're going to craft these segments. So I'm going to say here for segment, and now we're going to say in range. We're going from the onset of this phase, from the onset of the sleep stage, up until onset plus duration, so up until the end of the sleep stage, and the window length, so the size of the segment is going to be 3000. So I'm going to say here int onset, because this needs to be an integer, to int onset plus duration, and the step size is window length. And then the start of the sample is going to be equal to segment. So this is what we get here as the control variable. And then the end of the sample is going to be segment plus window length. Now we want to check if we are out of bounds. So we're going to say here if end sample is less than or equal to the length of the EEG channel 1. We're going to say window is equal to EEG channel 1 from start sample to end sample. And then to make sure that we're consistent here, the length of the window has to be equal to the window length, just as a secure statement here. Then we're going to add the window to the X data. And the Y data is going to be the mapping stage map applied to the description. So we're going to take the raw string from the description, we're going to map it to a number, and this is going to be our Y data. Finally, after all of this, we're going to say X is equal to NP array X data, and we're going to do the same thing for Y and Y data. So let's zoom out. This is what it looks like. We load for each subject the PSG file, the hypnogram, we load the first EEG channel, we load the annotations, we create a dictionary for mapping the strings to numbers, then we iterate over the labeled time segments, and we craft 30-second windows that we add as our training data with the respective classification. Actually, one thing that I forgot to mention is that onset and duration are in seconds, which means that we need to convert them to be seconds times 100 because that is our sampling frequency. So I'm going to say here onset times fs and onset times fs plus duration. And by the way, one more thing that I realized is before when I showed you that graph, I forgot to include sleep stage 4. So this is actually what it looks like without all these crazy jumps. So this is sleep stage 4 and REM makes a lot more sense. But yeah, so let us run this now. This will take some time. So the preparation is done now. It took 1 or 2 minutes, and we can take a look at the shape of X, and we can see that it has 68,180 samples that are 30 seconds each. And for Y, of course, we have the same number, but we only have a single output for each instance. It's also interesting to look at the distribution of Y. So we can say NP bin count of Y. This will show us how many different instances we have of the individual sleep stages. So most of them are going to be in waking state. A lot of them are in stage 2. Some of them are in REM, and we don't have too many in sleep stage 1, 3, and 4. Now, to actually be able to use this data in a neural network, we want to normalize it, and we also want to do a train test split. So I'm going to say now X is equal to X minus X dot mean to 0 center it, divided by the standard deviation of X. And then X train X test, Y train, Y test is equal to train test split on X and Y with a test size of 0.2, which means 20% of the data is going to be used for testing and 80% of the data is going to be used for training. Now, important, I also want to stratify here for Y, which means I want to have the equal distribution of classes when it comes to the split. So when we take a look at NP bin count for Y train, we can see this is the distribution. Maybe we can also divide it here by the length of Y train. And if I do the same thing with testing, we can see that the numbers are basically the same. Cool. So the last thing is we now need to get this into the PyTorch world. And for this, I'm going to say device is equal to, and I'm going to use my GPU if the GPU is available. Otherwise, you're going to fall back to CPU. So we're going to say device is equal to torch.device CUDA for the GPU if torch.CUDA is available, else CPU. And now we're going to take our NumPy arrays and turn them into tensors. So we're going to say xtrain is equal to torch.float tensor of xtrain. We're going to send this to the device, preferably the GPU. And actually, since we're only using a single channel, we're also going to add an unsqueeze here to add an additional dimension. Same thing will be done for test. And then for the Y values, we're going to do the same thing almost, but we're going to use long tensors, and there's no need to unsqueeze. Same for test. And by the way, change this to Y train and Y test. And of course, remove the plural. I think I need to run this again from the top. And there you go. We can check which device is being used. In my case, CUDA, so I'm using my GPU. And now we get to the interesting part, which is the model training. So I'm going to say now here, model training, and we're going to define our convolutional neural network by saying model is equal to nn.sequential. And in here now, we're going to define the individual layers. We're going to start with a convolutional layer, and we're going to use a 1D convolutional layer because we're working with time series and not with images. So nn conv 1D. Now we're getting one input channel, and I want to use 32 filters or kernels. So I'm going to output 32 channels, and the kernel size is going to be 50 in this first layer, and the stride, so to say the step size, is going to be 6. We're going to follow up this convolutional layer with a ReLU activation function to break linearity, so nn ReLU, rectified linear unit. Then we want to have a max pooling layer 1D with a kernel size of 8. Then I'm going to copy this. We're going to repeat the whole process, but this time, of course, we get 32 input channels. We want to produce 64 output channels. We want to set the kernel size to 8, and we don't need a stride. And again, ReLU, max pool, and then we want to flatten what we have. We're going to follow up this flatten layer with a fully connected layer, so NN linear. And we're going to have 64 times 6 as input here, and we want to output 128 neurons. We're following this up one more time with a ReLU. Then we're going to add a dropout for regularization with a probability of 50%. And finally, we're going to have a fully connected layer, which takes in the 128 signals and outputs exactly 6, because we have a waking state, REM state, and 4 sleep stages. So a total of 6 possible outputs. And that is our setup. Of course, feel free to adjust this. Feel free to play around different layer types. Maybe you want to do a recurrent neural network, whatever you want to do, feel free to play around with it. We're going to send all of this now to the device, so to the GPU. And then we're going to define our loss function and our optimizer. So the loss function is going to be our criterion. It's going to be the NN cross entropy loss. And the optimizer is going to be torch.optim.atom applied onto the model parameters and with a learning rate of 0.001. There you go. And now finally, we need to implement the training logic. I'm going to say I want to train for 10 epochs. That should be enough for the data set we have. I'm going to define a batch size of 64, and then we're going to iterate. We're going to say here for epoch in range epochs, set the model to training mode. We're going to keep track of the total loss of this epoch, which is going to start at 0. And then we're going to iterate over the batches. So for I in range, and we're going to start at 0, going up until the length of X train. And the step size is going to be the batch size. Then the batch X data is going to be equal to X train, starting from I, going up until I plus batch size. Send this to device as well. I'm not sure if we have to send it all the time, but I'm doing it all the time, so I don't have to run into the exceptions. Same thing is going to happen with the Y train data. Then we're going to zero out the gradients of our optimizer. So optimizer 0 grad. And then we're going to make a prediction with the current weights and biases that we have, with the current model parameters that we have. We're going to evaluate what the loss is, and then we're going to backpropagate it and take a step with the optimizer. So I'm going to say here outputs is equal to model applied on batch X. This is probably going to be pretty random in the beginning. So we're going to say loss is equal to criterion applied onto the outputs that we just generated and the ground truth, which is in batch Y. Then we're going to backpropagate this loss by saying loss.backward. And then we're going to take a step with the optimizer. And for each batch that we process, we're going to add to the total loss, whatever the loss of this batch was. And to keep track of the progress, I'm going to copy paste this now, just a simple print message, which prints for each epoch what the loss is. So now we can run this and we can see that we already start out with a pretty small loss, but it gets smaller and smaller and smaller. And there you go. Our model is trained. You can keep going if you want to. You can add more data. But now if you want to evaluate it on unseen data, what we do is we say model.eval with torch no gradient, because we're no longer training. The predictions we make are going to be equal to model applied onto xtest. Predicted classes are going to be equal to torch argmax predictions dimension equals 1. Get it back to the CPU and then turn it into NumPy. And we need this, of course, because scikit-learn works with NumPy. So accuracy is going to be equal to accuracy score applied onto y-test, which is also going to go back to the CPU and then turned into NumPy and predicted classes. So now we can take a look at the accuracy, and we have 92.607% accuracy. And in the beginning, we imported also the classification report. Actually, I would like to just look at the confusion matrix. I think that makes more sense. So let's go down here and say confusion matrix of y-test, CPU, NumPy, and then predicted classes. So we can see, although we have a pretty nice accuracy, for some classes, we still misclassify them quite often. So we see here for sleep stage 1, we oftentimes think it's a REM sleep state. And also for sleep stage 3, we oftentimes think it's 2, but it doesn't happen that someone is in sleep stage 2, 3, 4, and we think that he's awake. All right, now let us repeat all of this with 2 channels, with both channels. So I'm gonna change this heading here in the downloaded version or in the downloadable version, you're going to see both in the same notebook, but now here I'm going to say both channels. And the difference here is going to be EEG channel 1 and EEG channel 2 are going to be retrieved. Here we had PZ, OZ, and most of the stuff actually stays the same. The only difference is we now need two windows. So window 1 is going to be that, and window 2 is going to be the same thing on EEG channel 2. Then also we need to say window 1 is equal to that. We're just going to assume they have the same length. It is the case in this data set. And then instead of appending the window, we're going to append np stack. So we're going to stack these two windows together. I'm going to say list window 1, window 2, axis equals 0. I think that should be it for the most part. So I'm going to run this. This will now take some time again. So we're done now. If I take a look at the shape, we now have here an additional 2. For the Y, nothing changes. We can also go through the entire process here again. Now, one thing we need to change here, since we now have already this additional dimension, we don't need to unsqueeze. So I can actually remove this. Then we can run this again. And of course, in the model, we now get 2 inputs. So 2 channels is input, not 1. Besides that, we can keep everything as it was. I'm going to rerun the evaluation as well. And in order to not lose these results, I'm going to copy and paste these cells here so we can run them again, but we can keep the old results. Now the accuracy is 93.5% and the confusion matrix looks a bit better. Now we have more confusions here. So it seems like the accuracy shifted. So we have more correct conclusions or more correct classifications for these stages, but we have slightly worse results for these two. And also for the waking state. No, actually the waking state is also better. So only for sleep stage 1 and 2, we have slightly worse accuracy. But yeah, this is how you can predict whether someone's sleeping or not, and if they're sleeping, what the sleep stage is using EEG data and deep learning in Python. So that's it for this video today. I hope you enjoyed it and I hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Also, if you're interested in personal tutoring one-on-one, or if you're interested in any services related to machine learning, backend development, Python, anything that is covered on my channel, you can go to my website to the services or tutoring tab and check out what I have to offer. And besides that, don't forget to subscribe and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.